Welcome back to another tutorial on business statistics in Excel. In this tutorial, I'm going to talk about two famous discrete distributions named binomial and Poisson distribution. In probability and statistics, a random variable is simply a rule that assigns numbers to outcome of a random process. Some random variables can take any value within an interval like time or temperature, and they are called continuous random variable. It can be any number that has decimals and they are not discrete. Other can also take specific countable values such as 0, 1, 2, 3, and we call them discrete random variable. Binomial distribution and Poisson distribution are the frequency distribution built upon a discrete random variable. Let's start with the binomial distribution. A binomial distribution follows a Bernoulli process in which we have experiment consist of a sequence of n identical trials. For example, tossing a coin for n times, that would be a Bernoulli process. Each of this experiment has two outcomes, either success or failure. Think about tossing a coin when we have only two outcomes, either it's head or tail. The probability of success is denoted by p, and the failure denoted by 1 minus p. In the tossing coin example, we have 50% chance that get head, therefore we have 100% minus 50% chance that we can get tail. Also, the trials are independent. For example, each time that you toss a coin, the result doesn't impact the next time of trial or next time that you toss the coin. If we repeat this experiment for n times and record the result will build a frequency distribution known as binomial distribution. Let's look at this example. We toss 3 coins at the same time. Number of trial would be 3. Probability of getting head is 50%. Therefore, probability of getting tail is also 50%. X, the random variable, which is discrete random variable, is the number of heads in an trial. In the first coin, we can get head or tail. And second coin also, we can get head or tail. Let's assume that first coin is head, then second coin can be head or tail. So we have so far head, 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 tail, tail, head, tail, tail. Third coin also can be head or tail, right? So now for the 3 coin, this is the result. Head, 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 tail, head, tail, head, head, tail, tail, and so on. So in this experiment, we can see that we have 8 outcomes. Some of them have 3 heads, some of them 2 heads, some of them 1 head, and some of them 0 heads. Number of tail is 3 minus number of heads because now we are repeating tossing the coin for 3 times or tossing 3 coins at the same time. Now in binomial distribution problems, we are interested in finding the probability that we have x successes. Here success is defined as getting ahead. So we are looking at the probability of x being 1 or 2 or 3 or even 0. But it cannot be more than 3 because it's not possible. We are repeating this experiment for 3 times and it's not possible to get more than 3 heads, right? Now, as we increase the number of trial, we can measure the probability that we can have x number of heads when we toss n coins at the same time or we toss a coin for n times. So still, the number of trials is n, the probability of getting head is p, and we are looking at the probability of getting x number of successes or x number of heads in this n trial. So if we can count this number of possibilities, we can build the binomial distribution. This is the binomial probability function that basically builds the binomial frequency distribution. The first part of this function counts the number of experimental outcomes providing exactly x successes in n trial. This is basically a factorial combination of having x head from n possibilities. Next part counts the probability of particular sequence of trials outcome with x successes in n trial. Here x is number of successes, p is the probability of success in one trial, for example, probability of getting ahead on one trial, which was 50%, n is number of trial, for example, we tossed 3 coins, and f of x is the probability of x successes or x number of heads in n trial. And factorial is also the multiplication of n by all the lower values up to 1. Similar to any other distribution, binomial distribution has a mean and a standard deviation. The mean or expected value of the binomial distribution is number of trial multiplied by the probability of success. This gives the average number of success or expected number of success in n trials. Variance is np multiplied by 1 minus p. That's the dispersion of the number of success in n trial. But let's look at this function one more time and let's understand it within an example. In this example, we toss 3 loaded coins. Since the coins are loaded, the probability of getting head and tail is not equal. Let's assume that the probability of getting head is 40%, the probability of getting tail is 60%. We tossed these 3 coins, therefore the number of trials is 3, and x, a discrete random variable, is the number of heads in n trial. We are looking at the probability of getting 1 head among these 3 coins. Let's look at the result. So the first toss, or the first coin, can be head with the probability of 40%. So if this is the head, we are looking at having exactly 1 head, the other 2 can be tail. So we have head, tail, tail. The probability of getting head is 40% and for 1 head, and the others are 60%, and we are multiplying these probabilities. Therefore, the ultimate probability is 0.4 multiplied by 0.6 power 2. But this is not the only combination that we can expect for having 1 head. The next combination is if we have the head for in the second coin. So therefore, that would be 60% multiplied by 40% multiplied by 60%, still the same probability. Next combination can be tail, tail, head, and still 60% multiplied by 60% multiplied by 40%. That's still 0.4 multiplied by 0.6 power 2. So since we have 3 combinations now, we need to also incorporate this choosing one of these combinations into probability calculation. That's why we add this factorial component to the equation. This is basically choosing 1 head out of 3 possibilities or 3 coin. One of them should be head. This is basically counting all possible combination of having 1 head out of 3 coin or these 3 possibilities. In the function, we can see this part is that factorial combination. So here we have this factorial combination of choosing 1 head out of 3 coin, and then probability of getting head power 1, x is 1, and then probability of getting tail power 2, that is n minus 1. N is 3, x is 1, n minus 1 is 2. So basically, we have this binomial probability function being calculated in that example. Let's talk about Excel function and how we calculate this binomial probability function in the Excel. So this is the summary of what we discussed. This is the binomial distribution function. N is the number of trial and x is the number of success we are looking for in n trials. F of x is a probability that x success can appear in n trial. Back to our 3 coin example, n is 3. F of x is a probability that x head appears in 3 times of tossing a coin or tossing 3 coins. The probability of success, let's assume that is 40%. So now we can calculate these probabilities. What is the probability of getting 0 head when we toss 3 coins? In Excel, you can use binom.dist function. That would be binom.dist. So as soon as you write down the function, it asks you the input. First input is the number of success we are looking for, that's 0. Out of n trial, we are tossing 3 coins. The probability of getting head is 0.4%, and it's not cumulative because we are looking at only x being 0, just one number. So we put false, and that gives us the probability of getting 0 heads. I can repeat this function for the rest of the numbers, so that would be equal to binom.dist. So instead of typing 1, I basically can select this cell A19. That would be this cell. And then out of 3 trials with a probability of 40% and false again, because it's just the probability of 1. I can repeat this for the other numbers. There is no probability of 4 here, x getting 4, because we are tossing 3 coins. It's not possible to get more than 3 heads in this experiment. So now look at this binomial frequency distribution. There is 21.6% chance we get 0 head, 43% chance we get 1 head, 29% chance we get 2 heads, and a very small chance we get 3 heads. And that's because the coin is not fair, it's a loaded coin, and the probability of getting head is lower than probability of getting tail. That's how you address the probability questions in the binomial distribution. Something that I want you to notice is the reason we put false here. So if I ask you what is the probability that x is less than equal to 2, it means that I want you to tell me the probability that x is equal to 0, or probability that x is equal to 1, or probability that x is equal to 2. Note that I'm adding up the probability to answer this question. So probability that x is less than 2 is either 2, 1, or 0. So basically it's summation of this 3 number. I can add this 3 number, sum of these 3 numbers, to find that probability around 93%. So basically I'm adding this bar, and this bar. That's where the probability is cumulative, because I'm adding up separate probabilities. Instead of adding up those probability, I can use binom.dist 2 out of 3 trials with the probability of 40%. Now I can select true because I'm looking at a range given to x, not exactly one value, but a range of values. So I'm adding up different probabilities. That's where this distribution is now cumulative. So I put true, enter. So the same number, 93.6%. Another point that you need to notice when we are using Excel function is that binom.dist basically gives us the less than equal side. So if I'm looking at the probability that x is more than 2, then I need to rewrite it as 1 minus probability of x less than equal to 2. So look at here, either x can be more than 2 but not including 2, so here, or it can be less than 2. One of these two happening. So let me use this. Either x can be this side or this side, either more than or less than equal to 2. One of these two happen. So these two basically are complementary event. Therefore, the probability of one happening is equal to 1 minus the probability of the other happening. So now I can calculate this probability as 1 minus binom.dist 2 out of 3 with the probability 0.4 and true, because again I'm looking at x getting a range of value less than 2. So you can see that this is exactly this probability that x is more than 2, or same as probability of x being 3. If I say probability of x more than equal to 2, now I'm looking at different range. More than equal to 2 includes 2. So I'm looking at this area, more than equal to 2. So either this happens or this happens. Less than equal to 1. So if I want to use the binomial dist function, which gives me always the left side of the probability, I need to rewrite this function. That's equal to 1 minus probability of x less than 1. So either more than equal to 2 happen or less than equal to 1 happen. So now I can calculate this. Equals to 1 minus binomial.dist 1 out of 3 with the probability of 40%, and again true because again I'm looking at the range assigned to x, not exactly one value assigned to x. That's true, equal to 35.2. This is the base of the binomial distribution in Excel. You can basically answer any type of binomial distribution. When you see a question that has a concept of n trials and the concept of the result being success or failure to complementary outcome, then that's a binomial distribution. So in this example, we are tossing a coin for 5 times. What is the probability that number of heads is less than 3? So we are looking at the probability of x being less than 3. Again, binomial.dist gives us less than equal. So I can rewrite this as less than equal to 2. So less than 3 doesn't include 3. Less than equal to 2 is basically same as less than 3. Now I can use the binomial function. Number of success 2 out of 5 trial. Let's assume that the coins are fair, so there is 50% chance that you get head, and it is cumulative because I'm looking at the range assigned to x, not exactly one number. Now what is the probability that number of heads in 5 trials is between 2 and 4? This is the interesting one. Probability of x being between 2 and 4. So usually when we want to rewrite this function to be able to use the binomial distribution in the Excel, we need to know what number is included in this range, what number is not. So when we toss a coin for 5 times, either we get 0 head, 1, 2, 3, 4, or 5, nothing more than this. So the x being between 2 and 4 but doesn't include 2 and 4 is basically only here. It doesn't include 2 and it doesn't include 4. It's more than 2 but not including 2, and it's less than 4 but not including 4. That's basically 3. So I can rewrite this as probability of x being equal 3. Another way, and that's the general way you need to address this question, is putting the range of the values. So probability that x is between 4 and 2 is probability that x is less than 4, minus the probability that x is less than equal to 2. So look at here, the probability that x is less than 4 is this numbers. Let me highlight this. Less than 4 but doesn't include 4 is this orange area. Less than equal to 2 is this area. If I subtract the smaller area from the larger area, it gives me this area, which basically is the same as probability of 3. So now I can rewrite binomial.dist 3, 5, 0.5, and true, minus binomial.dist 2 out of 5 with probability of 50% and still true. This should be same as if you calculate probability of 3, but this way of rewriting is the general rule for rewriting this probability. This is really important, specifically in discrete distribution, because less than some number is not same as if we say less than equal that number. Each of this number are discrete and can be included or excluded from the probability. In the next tutorial, I'm going to talk about Poisson distribution, another type of discrete distribution.